Welcome to Tomorrow Unveiled.
It's great to be back.
Today is February 8, 2026, and I have to say, looking at just the stack of reports our research team dropped on my desk this morning, I feel like we're living in a timeline that was written by, I don't know, some sci-fi novelist who had way too much coffee.
That is a very specific vibe.
Yeah.
But I know exactly what you mean.
Right.
If you just glance at the headlines, it looks like standard space news, a launch here, a test there. But if you actually sit down and connect the dots, which is what we do here on Tomorrow Unveiled, you start to realize that this week, right now, it's statistically anomalous.
Anomalous how? What do you mean by that?
In volume and variety, we aren't just seeing a launch, we're seeing a convergence. Our research team has been tracking the launch manifest, the mission reports, the patent filings, and they're calling February 2026 a banner month.
A banner month.
But honestly, I think banner month it's too soft. It sounds like a sales promotion at a car dealership.
Right. Come on down for banner month. 0% financing on all orbital launches.
Exactly. This isn't that. This is a phase shift. We are moving from the era of heroic exploration, where every single mission is a custom-built, one-of-a-kind miracle, into the era of, industrialization.
That's a heavy word, though, industrialization. It implies factories and supply chains and standardization. It sounds a little boring. Are you telling me space is becoming boring?
I am telling you space is becoming infrastructure. And look, infrastructure is only boring until it breaks. Or until you realize it's the only reason civilization exists. Just look at the three major stories we're breaking down today. First, we have an artificial intelligence that just took the keys to $1 billion rover on Mars.
Which, let's be honest, sounds a little bit like the prequel to a movie where the robots take over.
We can get to the existential dread later, I promise.
Yeah.
Second, despite some very realistic delays, humanity is literally weeks away from a lunar flyby. And that mission is testing the systems for a permanent base. And third, and this is maybe the most crucial part for your industrial skepticism, the actual hardware for gas stations in space is finally being built and tested right now.
So wait, we have the pilot, which is the AI, we have the destination, the moon base, and we have the fuel.
Precisely. It's the convergence of artificial intelligence, advanced manufacturing, and, human ambition. Our research team actually found a NASA press release that literally refers to this period as a golden age of innovation.
A golden age. Okay, I like the sound of that. But I want to start with the robot on the red planet, because for years, we've heard about autonomous rovers.
We have.
I remember watching the Mars landings back in the day, and the engineers always said the rover could drive itself. So when I saw the report that AI is now driving the rover, I have to ask, is this actually new, or is this just, a software patch with a really good PR team?
That is the million-dollar question. And to answer it, we have to look under the hood. You're right that Perseverance and even Curiosity before it had something called AutoNav.
Right, AutoNav. It sounds like a GPS system for your car.
It kind of was, but it was a very geometric system. Think of it this way. The old AutoNav saw the world in math.
In math.
In pure geometry. It would take a stereo picture, identify a rock, draw a virtual box around the rock, and then calculate a path that didn't intersect with the box.
Okay. That sounds reasonable. Don't hit the rock.
It is reasonable, but it's dumb. It's purely geometric. It doesn't know what the rock is. It doesn't know if that flat-looking surface over there is solid bedrock or, deep, soft sand that could trap it forever.
So a shadow could look like a hole?
Exactly. To the old AutoNav, a shadow might look like a hole. A pile of loose regolith looks exactly the same as a solid slab of stone. It completely lacked context.
So it could see the obstacles, but it couldn't understand the terrain it was driving on.
It had no semantic understanding. And because of that, the human drivers at JPL, they're called rover planners, they couldn't fully trust it. They still had to micromanage huge chunks of every single drive because they were terrified the rover would drive straight into a sand trap.
And we know from history that sand traps on Mars, they're fatal.
They're rover killers.
Yeah.
Spirit, Opportunity, they all struggled with sand. If you drive into a ripple that looks totally solid but is actually just like fluff, your wheels spin, you dig yourself in, and you die. The old AutoNav could not tell the difference.
Okay, so enter the upgrade. The reports say this new system uses vision language models. Now, I use LLMs to write emails. Why in the world are we putting a chatbot architecture on a Mars rover?
It does sound counterintuitive, I get it.
Yeah.
But you have to remember, the underlying architecture of these modern AI models, like the Claude models that are referenced in our source material, It isn't just about text.
It's about patterns.
It's about pattern recognition. It's about tokens.
Okay, break that down for me. How does a token help you drive on Mars?
So instead of just seeing geometry, boxes, and lines, the new system digests these super high-resolution orbital images from the Mars Reconnaissance Orbiter.
The eye in the sky.
The eye in the sky. And it combines that orbital data with the rover's own camera data from the ground. It has been trained on millions and millions of images of Martian terrain. So now it doesn't just see a shape. It sees bedrock. It sees sand ripple. It sees hazardous boulder field.
It's labeling the world. It's adding meaning to the shapes.
It is perceiving the world. That is the fundamental shift. It's the difference between detection and perception. On December 8, 2025, the rover looked at this really complex field of sand ripples all mixed in with rocks. The old autonav would have just thrown up its hands and stopped, waiting for a human.
It would have just sat there.
It would have. But the new AI, it identified the firm patches of ground between the dangerous ripples, and it threaded the needle.
It navigated the maze all on its own.
It drove 210 meters in a that's a single Martian day. 2 days later, on December 10th, it did 246 meters.
Just to put that in perspective for you listening, 246 meters is over 2 football fields.
Yeah.
In one day on Mars.
Yeah. Historically, that is an absolute sprint. In the early days of the Mars exploration rovers, a good day was maybe 20 meters.
20.
20. So we are seeing an order of magnitude shift in speed and capability. And it's not just about bragging rights, setting a new distance record. It's about what our research team calls the latency terror.
Latency terror? That sounds like a horror movie.
It kind of is for a rover driver. Mars is far away. On average, it's about 140 million miles.
So the signal delay is huge.
It's huge. A radio signal takes about 20 minutes to get there and another 20 minutes to get back. That's a 40-minute round trip. You cannot joystick that. You can't drive it in real time.
Right. If you see a cliff ahead and you hit the brakes on your joystick here on Earth, the rover actually fell off that cliff 20 minutes ago.
Precisely. So you need autonomy.
Yeah.
But if we look further, to the icy moons of Jupiter or Saturn, the lag isn't minutes, it's hours.
Hours.
If we ever want to explore the outer solar system with rovers, we cannot have humans in the loop for every single driving decision.
Yep.
The robot must be able to think for itself.
So this is the proving ground. Mars is the test bed for the rest of the solar system.
It is. But I want to address your skepticism about safety, because you asked if this is just a PR stunt. The engineers at JPL are, they're legendarily paranoid.
As they should be.
As they should be. They didn't just upload the code and hope for the best. They used a digital twin.
I see this term popping up in manufacturing a lot, in all sorts of industries. What does it actually mean in this context?
So before the real rover moved a single inch on the real Mars, the AI's proposed path was fed into this hyper-realistic simulation on Earth. A virtual Perseverance drove over virtual rocks in a physics engine.
So like the world's most expensive, most accurate video game.
Essentially, yes, but a physics engine that is terrifyingly accurate. They checked over 500,000 telemetry variables. They simulated wheel slip, motor torque, thermal buildup in the joints, the current draw on the batteries for every single movement. They effectively forced the rover to hallucinate the entire drive in a completely safe virtual environment. And only after the digital twin survived the drive without flipping over or getting stuck. Only then did they beam the commands to the actual rover on Mars.
That is incredible. It's like precognitive driving. The rover lives the life before it actually lives it.
It's the only way you can safely deploy generative AI on a billion-dollar irreplaceable asset. You trust, but you verify in the simulation. And the consensus from our research team looking at all the data is that this represents a second-order shift.
That's important.
It changes the fundamental economy of exploration. We are moving from this old model of drive, stop, wait 24 hours for instructions, drive again, to drive all day, send back the data, wake up, drive again.
Which brings us right back to that industrialization theme you mentioned. If the robots can work a full shift without us holding their hands, they can start building things. But before we get to the building, we have to talk about the people.
The human element.
Because as smart as these robots are, let's be real, the public cares about astronauts. Absolutely.
Specifically, Artemis II. We have been talking about this mission for years. It feels like forever. This is the big return.
It's the first time humans will have left low Earth orbit since Apollo 17. And that was 1972.
Over 50 years, that's a long time.
It's staggering to think about, isn't it? An entire two generations really have lived their entire lives without a single human being venturing further than the space station.
So let's talk about the crew that is going to break that streak. We have Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen.
It is a phenomenal crew. And if you look at the official portraits, I mean, it is just a stark contrast to the Apollo era.
Apollo was remarkably homogeneous, to put it
It
mildly.
was. It was all white men, mostly test pilots. Here you have Christina Koch, who will be the first woman to travel beyond low Earth orbit. You have Victor Glover, the first person of color, and Jeremy Hansen, a Canadian representing the first international partner to leave Earth's immediate orbit.
It feels more representative of the planet that is sending them, which is a good thing. It really does. But we have to be realistic about the timeline. The original target was February 2026, this month. But the latest data from our research team indicates a slip. We're now looking at early March 2026.
What's the holdup? Is it the rocket, the capsule?
It's Florida, or more specifically, the weather in Florida. They ran into a cold snap during the wet dress rehearsals.
Okay, for those who don't speak NASA, wet dress rehearsal sounds like a costume party that's gone horribly wrong.
It does, doesn't it? It's the full countdown simulation. They roll the massive SLS rocket out to the pad. They load it with over 700,000 gallons of super chilled liquid hydrogen and oxygen. They count all the way down to T-minus 10 seconds. It's wet because of all that liquid fuel.
And the cold weather actually messed that up.
Well, rockets are giant metal cans. When it gets cold, metal contracts. Seals shrank. Valves can get a little sticky. They had some issues with the thermal expansion, or contraction, rather, of the supply lines. They also had to chase down some hydrogen leaks.
Hydrogen is notorious for leaking, isn't it?
It's the smallest molecule in the universe. It wants to escape. It will leak through microscopic gaps that water or kerosene wouldn't even notice. So delaying a few weeks to tighten all the seals, that is not just a good idea, it's prudent.
Okay, so assuming they launch in March, I have to play the cynic here for a second. We're sending 4 people 250,000 miles away from Earth, and they aren't landing.
No landing on this one.
They're just going to loop around and come back. It feels a little like driving all the way to Disney World, looking at the castle from the parking lot, and then just driving home. Why not land?
Because the parking lot is dangerous enough, we have to validate the vehicle first. Artemis II is, at its heart, a test flight. And the trajectory they're flying is fascinating. It's called a free return trajectory.
Free return. It sounds like a refund policy for a bad vacation.
It's actually a safety net. It relies purely on orbital mechanics.
Hmm.
Imagine throwing a ball so it loops perfectly around a pole and comes right back to your hand, without you having to do anything else. They're aiming the spacecraft so that the moon's gravity naturally slingshots them back toward Earth.
So if the engine dies on the far side of the moon...
They still come home. Gravity brings them home. Now, if they did a standard orbital insertion, where they have to fire the engine to slow down and circle the moon, and then the engine failed, they would be stranded.
Oh.
They would be stuck in lunar orbit until they ran out of air.
That is a terrifying thought.
It is. And that's why for the very first crewed flight of a new vehicle, you always use the free return. Gravity does the hard work. But this trajectory is going to take them deep. They are going 4,700 miles beyond the far side of the moon.
That is further out than any Apollo mission ever went.
Correct. Apollo hugged the lunar surface to prepare for landing. Artemis II is going into the deep dark. When they are at that furthest point, the Earth will look like a tiny blue and white marble. It's a psychological challenge as much as it is a technical one.
And a thermal one, right. I want to bring up the heat shield. Because after Artemis, the uncrewed test flight, there was a lot of concern about the char loss.
Ah, yes.
Yeah.
That was the big scare. The heat shield is designed to burn away. That's a process called ablation. It carries the intense heat of reentry away from the capsule. But on Artemis I, instead of burning away smoothly like, say, a piece of toast, it flaked off in chunks.
And chunks are bad.
Chunks are very, very bad. It makes the thermal protection uneven and unpredictable. NASA has spent the last year analyzing that data, and they have decided it is safe for Artemis II. But that's why this specific trajectory is so important. They are managing the entry speed and the heat load very, very carefully.
Because when they come back...
When they come back from the moon, they are hitting the atmosphere at Mach 32.
Mach 32.
That is 24,500 miles per hour. The friction from that generates temperatures half as hot as the surface of the sun. You cannot get that wrong. Not even once.
So Artemis II is the shakedown cruise. But if they aren't landing, what are they prepping for? What is the Disney World inside the park that they're aiming for later?
The Artemis Base Camp. The long-term plan, targeting the 2030s, is to establish a permanent foothold on the moon. And the visuals our research team dug up are just incredible. We are not talking about a flag and a footprint here. We're talking about dome-shaped habitats covered in lunar regolith.
Covering them in dirt.
Yeah, in moon dirt. It's for radiation shielding. The moon has no atmosphere, no magnetic field to protect you. You're completely exposed to solar flares, cosmic rays. The cheapest, most effective way to protect people is to just bury them under a few feet of soil.
Sounds cozy.
It's functional. And the location is key, the South Pole, specifically Shackleton Crater.
Why the South Pole? What's so special about it?
It's all about the shadows. The crater rims at the South Pole get perpetual sunlight, so you have infinite solar power. But the deep crater floors are in permanent shadow. They haven't seen a single ray of sun in billions of years. They're called cold traps.
And cold traps mean ice.
Exactly, water ice. And water is everything. Water is for drinking, obviously. But you can also split it, and you get oxygen for breathing. You compress the hydrogen, and that's rocket fuel. The South Pole is the only place on the moon where you can truly live off the land.
That really is the shift from a camping trip to an actual settlement.
It is. But getting to that settlement requires massive public support. It requires people who are engaged and informed, which actually brings us to, well, to you, the listener.
It does. We are diving deep today, but we absolutely can't do what we do here on Tomorrow Unveiled without our community.
So if you're watching us on YouTube and you're finding this breakdown of the future valuable, please take a moment to like this video and subscribe to Tomorrow Unveiled.
And consider hitting that new hype button. It really helps the algorithm find other people who are curious about space industrialization. And of course, turn on notifications so you never miss an update on the future.
And for our audio listeners, if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and a review for Tomorrow Unveiled. It truly helps us reach new listeners.
Absolutely. We read every one of the reviews, and we love seeing this community grow. Now, getting back to the hardware. We've talked about the moon, but getting there requires rockets, and getting to orbit is still, well, it's still hard.
It is incredibly difficult, and even the most reliable, most proven systems have hiccups. We saw that vividly on February 2, 2026, just a week ago.
You're talking about the Falcon 9 anomaly.
Yes. The Falcon 9 is the workhorse. It is the Ford F-150 of spaceflight. It launches constantly, almost every few days. But on the Starlink 1732 mission, there was a rare upper stage anomaly.
What actually went wrong? Because usually the reports are just vague, technical difficulties.
The investigation identified a gas bubble in the propellant transfer tube of the second stage engine.
A gas bubble? It sounds so minor, like, getting air in my kitchen faucet.
In your kitchen, it makes a sputtering noise.
Yeah.
In a rocket engine, it causes something called cavitation.
Cavitation.
When a gas bubble hits a turbopump that is spinning at 20,000 RPM, it collapses violently. It's like a tiny explosion. It can pit the metal, destroy the blades, or simply starve the engine of fuel. In this case, it prevented the Merlin vacuum engine from reigniting for the deorbit burn.
And the deorbit burn is what brings the rocket stage safely back into the atmosphere so it doesn't become dangerous space junk.
Correct. So because the engine couldn't reignite, the stage couldn't steer itself into a safe disposal corridor over the ocean immediately. It was stranded in a low, decaying orbit.
But the system didn't explode or anything.
No. And this is really a testament to the software and the engineering. The safety protocols kicked in automatically and passivated the stage.
Passivate.
It vented all its remaining pressure. It just opened the valves and let all the residual gas out into space. This prevents the tank from exploding later if it gets hit by debris or heats up in the sun. It made itself inert. It became safe.
So it became a safe piece of junk rather than a potential bomb floating around up there.
Exactly. But here's the industrial angle. The fleet was grounded on February 2. It returned to flight on February 7.
5 days later.
5 days. In the space shuttle era, a problem like that would have grounded the fleet for a year, maybe more. The speed at which they analyzed the telemetry, found the root cause with the bubble, checked the rest of the fleet, and got back on the pad.
That is just unprecedented.
And they needed to be fast because the launch schedule is absolutely packed.
It is. Crew 12 is launching on February 11, and interestingly enough, our research shows that date was actually moved up.
Which never happens. Launch dates always slide right, they never move left. Well, this one did. It was an emergency adjustment. There was a medical evacuation on the ISS back in January.
Yeah.
We don't have the specific details. Medical privacy laws apply even in space, but a crew member had to come home urgently. That left the station shorthanded.
So Crew 12 are the reinforcements coming in early.
They're the relief shift. It just shows how dynamic and responsive the logistics have become. But while Falcon 9 is doing all the heavy lifting, everyone is watching the new giants.
The heavy hitters, Starship and New Glenn. Let's talk Starship. We are looking at version 3 now.
V3.
Yeah.
It's taller. It holds more fuel. It uses the new Raptor 3 engines, which strip away a lot of the complex plumbing that caused headaches on the earlier models. They're targeting mid-March for the next flight test.
But the goal isn't just to fly up and splash down in the ocean, is it?
No, not at all. Yeah. The holy grail right now for them is orbital refueling. And cross-corroborated reports from our research team suggest a major demonstration is targeted for June 2026. Analysts are calling this the Mars Gate.
Mars Gate. It sounds very dramatic.
It is the single most important technology for deep space exploration. It's all because of the tyranny of the rocket equation. If you launch a massive ship like Starship, by the time it gets to orbit, it has burned almost all of its fuel just fighting its way up through Earth's gravity.
So it's basically sitting in orbit on an empty tank of gas.
Exactly. You can't go to Mars on empty. You have to send up a second Starship, a tanker, transfer the fuel in orbit, and top it off. If they can prove this works in June, the solar system opens up. If they can't, well, we're stuck in low Earth orbit.
And what about Blue Origin? They are in the mix here, too.
They are. They are prepping for the third flight of New Glenn in late February. And this is a big one for them because it's the first time they're attempting to reuse a booster.
Right. We've gotten so used to seeing SpaceX landing boosters. Now Blue Origin wants to join the club.
It's absolutely essential for the economics of spaceflight. If you throw away the rocket every single time, it's like throwing away a 747 after every flight from New York to London. The tickets would cost millions of dollars. If New Glenn can stick that landing, we have real competition, and competition drives prices down for everyone.
Which leads us perfectly to the next big segment. If prices come down and we can launch massive amounts of cargo, what are we actually doing up there?
This is that transition we spoke about in the intro. This is the industrial revolution in orbit.
Let's go back to that gas station concept. You mentioned the Mars Gate, but explaining how you refuel in space, that's where the physics gets really weird.
It gets very weird. The technical term is cryogenic fluid management.
Okay, let's unpack that. Why is pumping gas in space so different from, pumping gas at a Costco?
It's all about gravity. On Earth, gravity pulls the liquid to the bottom of the tank. The pump intake is at the bottom. You turn it on, you get liquid. It's simple.
And in space?
In zero gravity, there is no down, the liquid. It just floats. It forms these big blobs. It coats the walls of the tank because of surface tension. It mixes with the gas that's also in the tank to create this sort of foam. If you turn on a pump, you are just as likely to suck up a gas bubble as you are to get liquid fuel.
And as we just learned with the Falcon 9 anomaly, gas bubbles destroy pumps.
Exactly. So how do you fix it? The solution they are testing this year involves something called settling thrusters.
Settling thrusters.
It's a beautifully simple brute force solution. Before they turn on the main pumps to transfer the fuel, they fire these tiny little thrusters to push the spacecraft forward just a tiny bit. We were talking about maybe 0.001 Gs of acceleration.
How nudge?
Just a tiny nudge. But that little bit of acceleration creates just enough artificial gravity to push all the liquid to the back of the tank. The fuel settles, the gas rises to the front, and for a few minutes the physics behaves just like it does on Earth. Then you turn on the pumps and go like crazy.
It's amazing that the solution to this super high-tech fluid dynamics problem is basically just give it a little shove.
Sometimes the simplest physics is the best. But the infrastructure on the ground to support this is just massive. SpaceX is building an air separation plant in Texas.
An air separation plant, like for industrial gases?
Yes, because they need so much liquid oxygen, thousands and thousands of tons, that they can't just truck it in anymore. They are building a factory to literally suck air out of the atmosphere, freeze it, separate the nitrogen from the oxygen, and then liquefy it right there at the launch site.
That is industrial scale. You're not buying it anymore, you're making it.
It is. They're turning the launch pad into a refinery. And once you have that whole supply chain in place, the reusable rockets, the fuel, the reliable access, then you can start doing the really sci-fi stuff in space manufacturing.
Okay, why build something in space? Why not just build it here and launch it?
The tyranny of the fairing.
The nose cone of the rocket.
Right. Even on a huge rocket like Starship, the nose cone is only about 9 meters wide. If you want a telescope that is 20 meters wide, or a communications antenna that is 100 meters long, you have to fold it up like complex origami.
And complex origami usually jams or breaks.
It's heavy, it's complicated, and it's a massive failure point.
Yeah.
But what if you launch raw materials instead? Spools of carbon fiber, tanks of resin, and you build it up there. You can build it as big as you want. There's no size limit in a vacuum.
So who's actually doing this? Is this still just a PowerPoint presentation or is it real?
No, hardware is flying this year. DARPA is leading a program called NOM4D. We have two huge demos coming up. First, from Caltech, actually happening this month, February 2026. They're launching a free-flying robot.
Free fly meaning no tether, no umbilical.
No umbilical, no human joystick control. It's going to find a set of parts and assemble a truss structure, think high-tech Tinker Toys, completely autonomously. It'll snap the pieces together to create a rigid structure that's larger than itself.
And the second demo you mentioned.
That's from the University of Illinois, and it's coming up in April. They're working inside the Bishop airlock on the ISS. They are fabricating composites. They are actually curing resin and carbon fiber in the vacuum of space.
So they're not just assembling beams, they are manufacturing the beams themselves in space.
Yes. And the vision here is massive. If this works, we could get 100-meter wide antennas.
Why do we need an antenna that big?
For deep space communication, for one, or for situational awareness. You could track every single piece of debris in cislunar space. You could monitor the Earth's climate with insane resolution. You could even potentially beam solar power from orbit down to the ground. It completely breaks the size limit imposed by the rocket.
It really feels like we are moving the construction site to the final destination.
Precisely. And what's so fascinating is that while we are moving all this industry up there, the technology developed to do it is trickling back down here to Earth.
Yes, the spin-offs. This is always the part I use to convince my relatives at dinner parties that space exploration is worth the money.
It is the return on investment segment for sure.
So what do we have from this latest crop of research?
Okay, first let's talk about the Prithvi model. This is a collaboration between space agencies and IBM.
Is this another AI model?
It is, but it's specifically for Earth observation. And the feat here is just incredible. They took a detailed temperature map of the entire globe, and then they removed 99% of the pixels. They just deleted the data.
99%. So it's basically just a blank screen with a few dots.
To the human eye, yes, it looks like random noise,
Ah,
but the AI was able to accurately reconstruct the entire globe from that remaining 1% of data.
that is mind-blowing. It's filling in the gaps with physics.
It understands the physics of weather so well that it can predict the missing data. And this means we can do more with less. We can track wildfires like the Big Dixie Fire in California with faster updates from fewer satellites. We can map floods in real time. But the application that really surprised me was locusts.
Locusts. Like
Yeah.
the biblical plague.
Yes. In Africa, locust swarms can destroy entire harvests and cause widespread famine. This AI model is being used to predict their breeding grounds. It looks at soil moisture and subtle vegetation changes that are too small for humans to see from space.
So it finds the nursery before the swarm can hatch and launch.
Exactly. If you can find and disrupt the breeding ground, you stop the swarm before it even forms. That saves food. That saves lives.
That is incredible. From space pixels to food security, what else do you have?
Robotics. We talked about robots on Mars, but let's talk about a company called Picnic Robotics. They developed the software to help robots open hatches on space stations.
Opening a hatch sounds easy. I do it every time I open a door.
For a human, yes. For a robot, understanding a latch, a handle, the exact force required, and doing it all in zero gravity where you'll just float away if you push too hard, that is an incredibly complex physics problem.
Okay, fair point.
But they solved it. And now, that same software is being used in Ablua robots on Earth.
What does an Ablua robot do?
It cleans restrooms.
Wait, really? We went from the airlock of a space station to the public toilet.
We did, but think about it. Cleaning a restroom requires dexterity. You have to handle spray bottles, wipe down surfaces, open stall doors. The same code that figures out how to open a module on the gateway station is now scrubbing tiles.
It's solving a labor shortage here on Earth using technology developed for up there.
Exactly. But my personal favorite spin-off from this entire batch of research, it has to be the beer.
Mars beer. I saw this in the notes. You have to explain this to me.
So on Mars, the atmosphere is 95% carbon dioxide. If you want to survive, you have to capture that CO2 and process it. You need to separate the carbon from the oxygen to make breathable air.
Right, in situ resource utilization using what's there.
Well, the company took that specific carbon capture technology, the pumps, the filters, the separators, and they licensed it. And now craft breweries are using it.
To do what?
The fermentation process for beer produces a lot of CO2. Usually breweries just vent that gas into the air, and then they have to buy these huge tanks of commercial CO2 to carbonate the beer later.
Which is wasteful and expensive.
Exactly. This technology lets them capture their own exhaust, purify it using the Mars tech, and then recycle it right back into the beer to make it bubbly.
So the bubbles in the beer are recycled fermentation gas captured by Martian life support technology.
It saves money, it's much better for the environment, and it's a perfect example of trickle-down tech. Technology designed to keep astronauts alive on the red planet is now making your Friday night pint more sustainable.
I love that. I will never look at a bubble in my IPA the same way again.
It really connects the two worlds.
So let's try to wrap all this up. We have covered a massive amount of ground today.
It was a dense one for sure.
We started with an AI pilot driving itself across Mars, using these vision language models to see the world not just as shapes, but as meaning.
A shift that frees us from the tyranny of light-speed lag and really opens up the outer solar system for exploration.
We talked about the humans of Artemis II preparing to loop around the moon in a free return trajectory that pushes the limits of both safety and distance.
The first step in the shift from just visiting to actually staying, the precursor to the Artemis base camp.
We looked at the rocket Starship, New Glenn, Falcon 9, and the heavy industrial infrastructure being built to refuel them in orbit. We talked about settling thrusters and air separation plants.
The gas stations in the sky that make the entire solar system accessible.
And then we saw how all that tech lands right back here on Earth, fighting locusts, cleaning restrooms, and even carbonating our beverages.
The theme really is infrastructure. 2026 isn't just about the flashy headlines. It's about laying the foundation. It's the roads, the gas stations, the factories. We are watching the space age finally grow up.
It's an incredibly exciting time to be watching the sky. And as always, we want to hear from you.
We do. We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the concept of AI pilots on Mars. Would you trust them?
Yeah, imagine you are an astronaut on a long-haul rover trip, you're asleep in the back, and the AI says, I'm taking a shortcut. Do you let it? Let us know in the comments.
Before we go, I want to leave you with one final thought. A provocation, if you will.
Let's hear it.
We have spent this entire hour talking about how we are building all these things, how to refuel, how to print trusses, how to drive autonomously, but we haven't really grappled with what we will build.
What do you mean by that?
If we can actually manufacture 100-meter structures in orbit, if we have the gas stations, are we looking at the end of the International Space Station era where we live in these cramped tin cans and the beginning of actual space cities?
That's a big leap from a station to a city.
Is it? If the capacity is there, the ambition will follow. And here is the real question to chew on. If AI is already driving the rovers on Mars, how long until the AI is designing and building the cities for us before we even arrive?
Wow. Robots building our houses before we even pack our bags. That is definitely something to think about.
It's coming sooner than you think.
Thanks for joining us on Tomorrow Unveiled.
See you in the future.